GameSci.com. GameSci.com.
Simple partitioning. Partitioning is the divide in a divide and conquer algorithm named quicksort. What we're going to do is divide the data into two groups. It's a simple thing. What if we took the boys in the classroom and put them on the left and took the girls and put them on the right? Or we said tall students stand to the left and short students stand to the right. Whenever you divide a set of data into two groups, you are partitioning it. A partition is preparation for quicksort. It makes the quicksort faster. Just like you pre-rinse the dishes before you put them in the dishwasher so the dishwasher can wash them better, or you primer a surface before you paint it so the paint sticks better. Partitioning is the preparation phase for doing a quicksort, and I want to stress partitioning is critical to quicksort. It's basically 90% of the algorithm. Quicksort is known as the fastest algorithm for in-memory sorting. Quicksort also has an advantage over merge sort because it doesn't require an extra array like merge sort does. Merge sort requires more memory than quicksort does. Let's look at partitioning with a mind towards keeping it as the prep phase for quicksort. In simple partitioning, we're just going to pick a pivot value. We're going to choose a pivot value of 45 since it's roughly halfway between 10, the smallest value in our data, and 80, the largest value in our data. Let's use 45. If I were to partition numbers from 1 to 1,000, this technique would use 500 because 500 is in the middle of our data set. Choose a value in the middle of the range. That's it. Values smaller than the pivot will move to the left of the array, and values larger than the pivot will move to the right. Starting on the left side, look for large values that need to move to the right. Found one. 50 is out of place. If you compare 50 to our pivot, 50 is larger. Well, partitioning says everything that's large should be on this side of the array. 50 needs to move. It's out of place. Mark it with this purple arrow here, but don't move it yet. We're going to hold off on the move. Now let's switch to the right side and look for small values that need to move to the left. No, if you look at 60, it's fine where it is and should not be moved. Remember, the goal is to have large values on this side and small values on that side. 60 is just fine where it is. Let's move over to see what's next to 60 to see if we can find something that has to move. Looking on the right side of the array, looking for small values that need to be moved to the left. Let's find it. 40 is there. We found 40. Mark it with a red arrow. Now we have two values. We have 50 on the left, which is too big, and we have 40 on the right, which is smaller. Now we have two values to move. Let's swap those two values. Swapping requires a temp variable. Swapping 50 and 40 in the array, let's move the 50 to our temp variable. Once 50 is safely over in the temp variable, move the 40 as part of the swap. So the 40 in position 6 moved down and wiped out the 50 that was in position 0. But that's okay. We don't mind losing that 50. It's safely in the temp variable. Move the 50 as part of the swap with 40. The arrows show the position of the swap numbers. We had a 40 over here and a 50 over there. Now our swap is complete. Let's resume our search for out-of-place numbers by moving towards the middle. See this red underline? We don't need to look at these two numbers anymore. Forget about them. Let's scan between 20 and 70 and find numbers that need to move. Picking up on the left, let's look at it for a large number that needs to move right. The answer is no. 20 is fine and should not be moved to the right. Let's keep moving towards the middle, looking for large values. Moving towards the middle, look for large values that need to move right. Found one. 80 is out of place and should be moved to the right. Let's mark 80 with a purple arrow, but don't move it yet. Looking on the right side, we're looking for small values that need to move left. No, 70 is fine where it is and should not be moved. Let's move to the next value to its left, looking for small values. Looking on the right side, looking for small values that need to move left. We found one. 10 is definitely out of place. 10 is smaller than the pivot. It needs to be moved to the left. Mark it with a red arrow. At this point, we have two values. We have 80 on the left and we have 10 on the right. Those two values need to swap. Swapping requires a temp variable. We'll move the 80 into the temp variable. This is part of the swap of 80 and 10 in the array. Now we can move the 10 over and wipe out the 80 that was right there. But we don't mind overwriting the 80 because it's safely in the temp variable. Move the 80 as part of the swap with 10. The arrow showed the position of the swap numbers. 10 and 80 just changed positions. We need to resume the search for out-of-place numbers by moving towards the middle. Now we'll scan between 30 and 30. The only position we haven't looked at left is 30. We still need to look to see if swapping needs to occur. We're looking for large values on the left and small values on the right. Picking up on the left, looking for large values that need to move right. No, 30 is just fine and should not be moved to the right. Keep moving towards the middle and look for large values. Moving towards the middle, we look for a large value that needs to move right, and we found one. 80 is out of place and needs to be moved to the right. We'll mark it with a purple arrow, but once again, do not move it yet. Picking up on the right side, we're looking for small values that need to move left, and we found one. If we move the right arrow, 30 is out of place and needs to move to left. Now notice my question marks here. Something has happened. If you look closely after we mark with a red arrow, we notice that the red and purple arrows have crossed. There's no swap done when these two arrows cross. Purple started on the left. Red started on the right. They have crossed positions. When they cross positions, we do not swap. When the arrows have crossed, the partition is done. Everything to the left of this red line is less than 45. Everything to the right of this red line is greater than the pivot 45. And the purple arrow, which started on the left, is what we call our partition point. Everyone to the left is less than the pivot. Everything to the right is greater than the pivot. That's our partition point. Our partition is complete. If you look closely, everything that's less than the pivot is on this side. Everything that's greater than the pivot is on that side. That's what a partition is. A simple division of the data into two groups. A small group on the left and a large group on the right. That is simple partitioning. Let's look at a simple partitioning trace. Let's look at the code that divides the data into two pieces. Now this is the same data and the same algorithm that we just looked at. Now that you have a logical picture of what partitioning does, small to the left, greater than to the right, let's go ahead and trace some code that does it. We'll set up some variables here. Pivot to 45. Once again, this is sort of a pivot that is in the middle of our data. We know our data goes between 10 and 80, so we pick the pivot 45 as the sort of data in the middle, the pivot in the middle. We'll set left equal to -1. That's the start of our scan on the left side. We'll set right equal to 8. That's the start of our scan on the right side. Left is less than the start of the array 0. Right is one more than the end of the array 7. What we're going to do here is a lot of prefix notation. So we're starting left and right beyond the end of the array. These normally would be parameters to a method, but I just want to show you the code. So I don't want to write a whole method here and talk about parameters. We don't typically hard code these values. You don't hard code a pivot of 45. You don't hard code the left as -1. You don't hard code the right as 8. But in order to show you in a small amount of code how it works, I'm using this technique of hard coding just to make this example a little clearer. When we get to the full version of simple partitioning, these will be parameters instead of hard-coded values. Also, let's start the loop. Let's do while left is less than right. Now, left is -1. Right is 8. Well, -1 is less than 8 is a true statement. We're going to go inside the code. Remember what partitioning does. It starts on the left and looks for a large value to move. Well, that's what this while loop is doing. Starting on the left with a prefix ++, it tests whether 50 is less than 45. Is 50 less than 45? Well, that's a false statement and the loop will execute. What this false indicates is we have found a large value on the left. 50 is greater than the pivot, so we want to exit this loop. Notice the prefix ++ on the left means left moves to 0 before we do the check. Don't swap yet, but notice how left equals 0. Notice our purple arrow. That tells us we will be swapping 50 in the future. Dropping down to the second loop, while the array sub minus right is greater than the pivot. Starting on the right side, look at this arrow, and a prefix of minus, we're going to test whether 60 is greater than 45. Well, that's a true statement. When this statement is true, this loop is going to spin back up and do it again. 60 is on the proper side. We don't want to move it. What we want to do is execute this loop again. Note the use of the semicolon. This is a bit tricky. Normally, this is a bad place to put a semicolon. But in this case, we want to do a minus right again. Since there is this prefix minus right here, this loop will change when it spins back up again. Very tricky code. Don't try this unless you understand what you're doing. The minus right will execute a second time. When it executes a second time, it will move down to 6. When right moves down to 6, we're looking at the 40. We're going to test whether 40 is less than 45, and that is very much a false statement. That means the loop will exit. When this loop exits, it means we found a small value on the left with right equal to 6. The red arrow shows you what we're looking at. It tells us we have found a small value 40 at index 6, which needs to swap with the large value 50 on the left. We have now located our two numbers that need to swap. 50 and 40 need to change places. If left is less than right, 0 in left less than the 6 in right is a true statement, so we need to do the swap of 50 at index 0 and the 40 at index 6. We all know how the swap works, so I'm not going to show you the swap line by line. But the 50 that was in position 0 moved to temp. The 40 in position 6 moved to index 0. We'll move the 50 next, but what we're doing here is pass by reference of an array. We're swapping left and right in this array. To finish the swap, we move the 50 from temp to index 6. We hit the end of the loop and we're going to go back up and spin in this loop again, looking for large on the left and small on the right. I hope that doesn't confuse you too much. All we did is a swap of 50 and 40 there. And now it's time to loop back up. 0 less than 6 is still a true statement. I have a 0 in left. I have a 6 in right. We're going to pick up on the left and look for large values that need to move to the right. No, 20 is just fine. We're looking at this 20 right now with this while loop here, and it's just fine where it is. Do not move it to the right. We're going to hit this semicolon, come back and do this ++ left again, and look for another number that needs to move. Spinning in this loop, the plus plus left has said go to position 2. At position 2, look what we found. We're looking for large values that need to move to the right. We found one. 80 is out of place and should move to the right. Let's mark it with our purple arrow. Left equals 2. That's where we want to do it. But we're not swapping 80 yet. What we do in partitioning is we get a 2-for-1 swap. When we have two numbers out of place, a large number on the left and a small number on the right, when we have two numbers out of place, then we swap them. So looking at the right, notice the red arrow here. Looking at the right, we're looking for small values that need to move left. No, 70 is fine where it is and should not be moved. What we need to do is when we hit this semicolon, we're going to loop back up here and do the minus minus right. Notice how right is going to change. Right is at 50. We're going to change it to 4. The minus minus right says look at this position. Looking on the right side, look for small values that need to move left. Well, we found one. 10 is out of place and should be moved to the left. Mark it with the red arrow. Now we have two numbers that need to swap. We have 10 on the right, which needs to go this way. We have 80 on the left, which needs to go that way. We're going to swap. And we're going to get 2 for the price of 1. 80 is going to move to a better spot. And 10 is going to move to a better spot. Checking our if statement, left, which is 2, is less than right, which is 4. That is a true statement. We're going to swap 80 at index 2 with 10 at index 4. We all know how a swap works. The 80 is going to move to the temp variable. The 10 at index 4 is going to move to where the 80 was at index 2. This is passed by reference to an array. We're going to change the positions of 10 and 80. Completing the swap, the 80 moves back up into the array to its proper position. The swap with 10 is complete. The arrows, purple and red, show you the position of the swapped numbers. Let's resume the search for out-of-place numbers by moving towards the middle. We are going to scan index 3 here for large values on the left and small values on the right. 2 is less than 4. That is a true statement, so we're going to continue the execution of the loop. Pick up on the left. Look for large values that need to move to right. Looking at this 30, no, it's fine. It should not be moved to the right. Keep moving towards the middle, looking for large values that need to be moved. The plus plus left here moved left to 4. That's why my purple arrow moved to 4. Moving towards the middle, looking for large values that need to be moved to right. We found one. 80 is out of place and may be moved to the right. Notice my question marks. Remember, we don't move until we find 2 out of place. We'll mark it with the purple arrow, but we will not move it yet. Moving down to the second inner while loop. Looking on the right, we're looking for small values that need to be moved to left. We've moved to the right. We found one. 30 is out of place and needs to be moved to left. Notice my question marks. Guess what? We mark it with a red arrow, but notice that the arrows have crossed. When the red arrow and the purple arrow cross, we're done. We don't need to do a swap. Do not swap when these arrows have crossed. Look at our if statement now. Left is 4, right is 3. The arrow has crossed. When the arrows have crossed, the partition is done. Everything to the left of the red arrow is less than 45. Everything to the right of the purple arrow is greater than 45. We do not need to do a swap. And that if statement going to false says skip the swap. When we hit the end of the while loop, we'll loop back up. But we know what's going to happen. The arrows have crossed. The partition is done. We don't need to do a swap, and we don't need to continue. 4 less than 3 is very much a false statement. The partition is done. The while loop will exit. Once again, everything to the left of the red line is less than 45. Everything to the right of the red line is greater than 45. The purple arrow, which started on the left, is what we call the partition point. We are very certain that if you are on the left of this arrow, you are less than the pivot. And if you are at this arrow or on the right, you are greater than the pivot. That's a partition. Small numbers to the left, large numbers to the right. This is the essential step in doing a quicksort. To quicksort these numbers, I will then just partition the left and right side, and eventually the numbers will come up in order. Improved partitioning. Let's look at a slightly better way to partition the data. Remember, partitioning is the divide in a divide and conquer algorithm that involves quicksort. Divide data into two groups. Partitioning is simply an act of dividing something into two groups. Partitioning is a preparation for quicksort, which makes it faster, like pre-rinses on the dishes before you put them in the dishwasher, or primer on a surface before you paint it. Partitioning is a step to improve quicksort. And all we're going to do on this slide is look at a slightly better way to partition the data than our simple partitioning. In this algorithm, the pivot value is always going to be the last number. Since 30 is the end of the partition, 30 will be the pivot. Remember, the last time we did it, we picked a number that was in the middle of the range of numbers. We picked 45 sort of out of thin air because it was between 10 and 80. This time, we're going to pick an actual value in the array, the number at the very end. Also, this allows 30 to be excluded from the scan. On the right, we'll start with the 40 and move towards the middle. And then at the end of the scan, 30 will be placed into the partition at the proper position. So it's just a minor tweak to the previous algorithm. Use the number at the end as our pivot value. Starting on the left, let's look for large numbers that need to move right. We found one. 50 is greater than 30. 50 is out of place and should be moved to the right. Let's mark it with the purple arrow, but don't move it yet. Remember, we do 2-for-1 swaps during partition. We don't move the 50 until we find a number on the other side of the array that needs to swap with 50. Looking at the right, remember we're not looking at 30, we exclude 30. Look for small values that need to move left. No, 40 is fine where it is. 40 is greater than the pivot. It belongs on the right side. It should not be moved. Let's move to the next value to its left. Moving towards the center, looking for small values that need to be moved left. No, 70 is fine where it is. It should not be moved. Move to the next value, looking for someone to swap with 50. Moving to the left, looking for small values that need to move left. Found one. 20 is out of place and should be moved to the left. This value is smaller than the pivot. It needs to go on the other side of the array. This value is greater than the pivot. It needs to go to the right. We'll mark it with a red arrow, and it's time to do a 2-for-1 swap. Do you understand what I mean when I say 2-for-1 swap? I have a number that's out of place on the left. I have a number that's out of place on the right. When I swap them, they're both moving to a better position. Swapping requires the temp variable, so the 50 will be saved into the temp variable. Now I can move the 20 over to where the 50 was as part of the swap with 50. And of course, the 50 goes back into the spot where 20 was. The arrows show the position of the swap numbers. 20 and 50 have changed place. Notice how 20 is less than the pivot. It should be on the left side of the array. Notice how 50 is greater than the pivot. 50 should be on the right side of the array. We'll resume the search for out of place numbers by moving towards the middle. We need to scan between 10 and 60. That's why I left the arrows here. We don't have to look at those positions anymore. Our next pass through this algorithm is only going to search between 10 and 60. Resume search for out of place numbers by moving towards the middle. Scan between 10 and 60 for large values on the left and small values on the right. Picking up on the left, we're looking for large values that need to move right. No, 10 is fine. It should not be moved to the right. Keep moving towards the middle, looking for large values. Looking to the left, looking for large values that need to be moved to right. We found one. 80 is definitely out of place. 80 is larger than the pivot and needs to move right. Mark it with a purple arrow, but as always, don't move it yet. Find a corresponding number before you do the swap. Looking to the right, we're looking for small values that need to move left. No, 60 is fine where it is and should not be moved. Move to the next value to its left. Moving to the left, we're still looking for small values that need to move left. No, 80 is fine where it is and should not be moved. Let's move to the next value to its left. Looking on the right side, look for small values that need to be moved to left. We found one. 10 is out of place and may be moved, but notice my question marks. Mark it with the red arrow and notice that the arrows have crossed. When the purple and the red arrows cross, there's no swap. We're done with this scan. When the arrows have crossed, the partition is almost done. Everything to the left of the purple arrow is less than the pivot 30. Everything to the right of the purple arrow is greater than the pivot 30. The purple arrow, which started on the left, is our partition point. Now we're going to add a new step. The new step is to swap the pivot with the purple arrow, the 80, and it's perfect. Notice how I had this glowing red arrow here. The last thing this improved partitioning algorithm does is it moves that 30 to where the purple arrow is. Simple swap. Swapping requires a temp variable. We'll move the 80 into the temp variable and we'll swap with 30 in the array. Once again, we're getting a 2-for-1 swap. The 80 and the 30 both move to better positions. The 30 moved down and replaced the 80 there. We took the 80 and put it back to where the 30 was. Boom. The arrows show the position of the swap numbers. The partition is done. Notice the pivot value 30 is in the perfect position. Now, what do I mean by perfect position? That's exactly where 30 should be if we sorted this data. Everyone to the left of 30 is less than 30. Everything to the right of 30 is greater than the pivot of 30. The purple arrow, which started on the left, is now the partition point. Furthermore, 30 is exactly where it should go. Look closely at this data. Will you ever have to move 30 when you're sorting it? No, 30 is in the perfect sorted position. That's important because we're not going to have to look at 30 again. With the partition done, it's not hard to see if we recursively partition the left side, excluding 30 because it's perfect, it will also become sorted. All we have to do is run a partition on these two numbers, and those two numbers will become sorted. When the partition is done, it's not hard to see if we recursively partition the right side. Once again, we don't have to look at 30. It's perfect. This right side will also become sorted. Partitioning does not have to evenly divide the groups of equal size. However, it does improve performance when they are near equal. Notice how we only have two numbers on the left side, less than the pivot 30. Notice how we have 5 numbers on the right side, greater than the pivot 30. That's okay, not a problem. We'd like it to be more towards the middle, but it doesn't have to be in the middle. What I really need you to visualize is if I do a partition on the left and right side, this data will come out in order. There is one more partition algorithm to look at that tries to improve the selection of a good pivot value, and that's called median of 3, and we'll move on to that next. Median of 3. Using the last value as a pivot is not always the best idea. If we use this 20 up above as a pivot, it would result in a lopsided split. If the last number was 10 or 70, it would be even worse. If you pick this as your pivot value, sometimes you get a bad pivot value. Median of 3 says look at 3 numbers: the first number, the middle number, and the last number, and pick the median of 3. Median of 3 is a subtle speed improvement to make sure we use a better pivot. Makes a difference when sorting millions of numbers, not so much when sorting 7 numbers. This is how median of 3 works. Looking at 3 numbers, the first, the middle, and the last number, I've highlighted them in red, the first, the middle, and the last number. Pick 40 as the median or middle of the 3. If I had to pick a pivot between 40, 60, and 20, I'd pick 40 because it's in the center. Good pivot values lead to faster sorting. Choosing the best of 3 improves performance. Also, since we're looking at 3 values anyway, let's move them into their proper place. All of these are small speed improvements that add up when you're sorting millions of numbers. So what we're going to do is move the 3 values to their sorted positions. Since 40 greater than 60 is a false statement, we'll leave 40 and 60 alone right where they are for now. Let's move the 3 variables to their sorted positions. Since the 40 and the 20 were out of place, since 40 is greater than 20, we're going to swap them. Now what we just did is we temporarily moved the pivot to here. We'll move it again shortly. Moving the 3 variables to their sorted positions, since 60 is greater than 40, we swapped them. What we ended up doing here is sorting 20, 40, and 60 to their proper places in the array. At this point, 20 is on the correct side of the partition. 60 must be on the correct side of the partition because our pivot value is 40. Now, there'll be no need to look at 20 and 60 when doing the partition. One more swap. We're going to move the pivot to the next to the last position. See that 40? We're going to move it to where that 70 is. The pivot 40 and the next to the last position 70 just swapped their positions. Now we can also exclude 40 from the partition scan and swap it at the end to its perfect position. The actual scan for large numbers on the left and small numbers on the right can start now. 20, once again, does not need to be scanned. It's there because it was less than the pivot 40. 60 also does not need to be scanned. It's there because it's greater than the pivot 40. And then again, 40 doesn't need to be scanned. It is the pivot value. Just like with the last algorithm, we're going to exclude the pivot from the scan and then move it to its perfect position when we're done. The actual scan while doing this partition will occur between 50 and 10. 50 on the left and 10 on the right. Starting on the left, let's look for large values that need to move right. Found one. 50 is greater than 40, the pivot, and should be moved to the right. Let's mark it with a purple arrow, but do not move it yet. Starting on the right, let's look for small values that need to move left. We found one. 10 is less than 40, which is the pivot. It should be swapped to the left. Mark it with the red arrow, and it's time to do a 2-for-1 swap. What do I mean by a 2-for-1 swap? 2 numbers are moving. 50, which is on the wrong side, needs to go. 10, which is on the wrong side, needs to go. When we swap these 2 numbers, we'll get both numbers moving to a better position. The arrows show the positions of the numbers that need to be swapped. Swapping requires a temp variable. The 50 will move and be safely stored in temp. 10 then shifts over to where the 50 was. To complete the swap, move 50 to the position of where 10 was. The arrows show the position of the swap numbers. It's time to resume the search for out-of-place numbers by moving towards the middle. We will now scan between 30 and 70 for large values on the left and small values on the right. The arrows don't need to be compared anymore. Those are on the correct side of the partition. Looking on the left, we want to find large values that need to move right. Nope. 30 is fine. It's less than the pivot 40. It's where it should be, and don't move it. Move to the next value to its right. Looking on the left, we found a large value that needs to move right. 70 is greater than 40. It may be moved to right. Notice my question marks. Remember, you don't do the actual swap till you find its counterpart on the other side. Mark it with a purple arrow, but do not swap it yet. I have a feeling we're not going to swap it. Looking on the right for small values that need to move left, 70 is fine where it should be. It should not be moved. Let's move to the next value to its left. Looking on the right, looking for small values that need to be moved left, we found one. 30 less than 40, the pivot. It may be moved to left. Notice my question marks. Mark it with a red arrow. Arrows have crossed. The red arrow and the purple arrow have crossed. That's your indication that no swap is needed. We are nearing the end of the partition. The scan is done. We've got one more step to do. Can you remember what that last step is? When the arrow is crossed, the partition is almost done. Everything to the left of the purple arrow is less than the pivot 40. Everything to the right of the purple arrow is greater than the pivot 40. The purple arrow, which started on the left, is our partition point. This is that special or new step I was talking about. Swap the pivot 40 with the purple arrow 70 and it will be in the perfect position. Watch it. We're going to take the 70 as part of the swap and move it to the temp variable. When we're swapping 70 and 40 in the array, we're going to get a 2-for-1 swap. Both 70 and 40 are going to move to better positions in the array. Move the 40 as part of the swap with 70. The pivot is now in the perfect position. All values to the left of 40 are less than 40. After this 70 gets moved into position, all values to the right will be greater than 40. 40 at index 3 is perfect. We can exclude it from future partitions. The 70 is moved up. You can clearly see that everybody on the right side of the pivot 40 is greater than 40. All we need to do now is use recursion to conquer the left side. Let's go ahead and use recursion and say, hey, partition this left side. Recursively call the method to quicksort the left side. You can exclude 40. It's in its perfect position. With the partition done, it's not hard to see if we recursively partition the left side, not including 40, it will become sorted. Median of 3 does have a special rule that says manually sort if the partition has 3 or less elements. So when we call partition on this side, the 20 and 10 will swap as part of the median 3 special rule. We'll manually sort the 3 or less numbers. Do you see how 40 is in the correct position? Look how this goes. 10, 20, 30, 40. 40 is exactly where it should be. With that partitioning done, it's not hard to see if we recursively quicksort the right side, once again excluding 40, it will also become sorted. Median 3 has this special rule that says manually sort when you're down to 3 or less elements. Let's manually sort these 3 numbers and see what happens. The 60 and 70 swap as part of the median of 3 special rule. Manually sort a partition of 3 or less numbers. Notice how we sorted both sides of 40 without even looking at 40. Moving the pivot 40 at the end of the partitioning is why 40 is in the perfect spot, or perfect position. If you look closely, our data is now sorted. I did a median of 3 partitioning, then I said quick sort the left side and sorted it. Quick sort the right side, sorted it. Both sides of 40 are sorted, my data is sorted. The quick sort algorithm says partition using the median of 3 algorithm, then quick sort the left side. When that's done, quick sort the right side and you're done. Partitioning is the essential ingredient to doing a quick sort. Quick sort is the fastest sorted algorithm for in-memory sorting. Merge sort can give it a run if the data is outside of RAM memory, but quick sort is generally considered the fastest for inside RAM memory sorting.